it's optional, but it's, yeah, getting advice is sometimes painful, but often useful. So I highly recommend it. And a lot of what you can do in this degree is also interact with others and get some feedback. So I highly recommend it, but it is optional. It is optional. All right. So we're here in these two notebooks. They'll also be on GitHub. And this one, we dealt with it for a bit, least squares for data science. And hopefully we can complete this tonight in the next 60 minutes. And even move on to Gaussian distributions and covariance. And if we don't have time for that, we'll do that next week. So what we have here, just to keep in mind, something that appears at first simple is we have some matrix A, and we have a right-hand side B, nothing special in that. And we're going to speak about least squares for trying to approximately solve AX equals B. Of course, you've had this in the quiz, but there's just a few missing bits in least squares that we'd like to do, and some of them are actually very practical, relating to things that you'll be using as an applied data scientist, specifically ridge regression. Who's heard of ridge regression? Has anybody heard of ridge regression? I'll type it in the chat as well. So ridge regression, we're going to see this in the next minutes. Has anybody heard of ridge regression or no? I don't see. Oh, okay, there is some. Good. Okay. All right. So first is first. Let's be slightly formal, just a bit more, even though this is a post quiz lesson. So you remember the SVD factorization. So we have a matrix A, and we can factor it as a matrix U with orthonormal columns, a diagonal matrix sigma, and a matrix V, and we multiply V transpose with orthonormal columns. Now, it's actually useful to, just like, I think we've done this before, we've stuck the QR factorization in the pseudo inverse, right? This beautiful formula here is a pseudo inverse, is a formula for the pseudo inverse when the columns of A are linearly independent. Okay. So let's see what happens. Let's just go with it. Let's see what happens when we stick the SVD in the pseudo inverse. Okay. So I have here this pseudo inverse, and this is kind of a fun calculation. So I just stick A transpose. So A transpose, you see this thing transposed is this thing, V sigma U transpose, right? So now why don't I have a sigma transposed here? Why don't I have a sigma transposed? Because sigma is diagonal, okay? Now, there are different forms of the SVD, and sometimes, I mean, sigma certainly has only things on the diagonal. Sometimes it has different dimensions depending on what we meant with dimension of V and U. But yeah, sigma is basically diagonal. So then, of course, U transpose U, this guy is going to vanish because U, I wouldn't say that U is an orthogonal matrix, but U is a matrix with orthonormal columns, so U transpose U is the identity. So then what we have is we have here a sigma squared. Okay, and this is in this -1. So when we do this -1, this inverse here, the next step here, you've got remember when you do, and we've done this all the time with A, B transposed is B transpose, A transpose, but the same for inverses, right? When you have a matrix inverse, you also switch the order. So here you have V minus transposed, sigma -2, V minus T. Okay, and this multiplies VU sigma, and now the V minus T and the V, what happens here? So the V minus T and the V, why do I have a mistake? Sorry, this is a mistake. This is not V minus T. This is just V minus 1 beta. Okay, so because we had here a V on the left-hand side, so V minus 1. The V inverse cancels the V, and the sigma minus 2 cancels this one of the sigmas to become a sigma minus 1. So the thing I want to show you here is now this formula. So this is a formula for a dagger for the pseudo inverse, which is given in terms of the singular value decomposition. And what it tells us is you take your singular value decomposition. This is singular value decomposition, U sigma V transposed. But what you do is you have a V sigma inverse U transposed. Now, what's the matrix sigma inverse? What does the matrix sigma inverse have? Sigma is a diagonal matrix. So what's sigma inverse? What does sigma inverse have? So C is a matrix with singular values on its diagonal. It's still diagonal with one on the sigmas. Yeah, one on the, yeah. And no need for the det, etc. But just one on the sigmas. Good. Okay, so the nice thing about this formula, this is the more general formula for the pseudo inverse that does not require this A transposed A to be invertible. Remember, so when we spoke about the pseudo inverse, we always wanted A transposed A to be invertible. But this one will always exist and will agree with this one, even if A transposed A is not invertible. Okay, so at least the singular value decomposition gives us a way to say what is the Moore-Poinreau pseudo inverse, left pseudo inverse, when the matrix A has linearly dependent columns, when it's not a matrix of zero null space, when it's not a full rank skinny matrix. Okay, so just to see this in action, let's do an SVD on this matrix A. Okay, A is the same one we had above. And I'm going to do the pseudo inverse on the matrix A. Okay, this is still not the case where A, if in this specific case, if I do rank of A, I believe it's rank 3. So A has now linearly independent columns. But let's still just see that this formula works. V sigma -1 U transposed. So this is a pseudo inverse of A, which we don't know how Julia computed it. I mean, maybe it computed it this way, or maybe it computed it this way. It actually depends on what's in the matrix A and the way it computes it. Okay, it often uses QR factorization. Okay, and now let's take the matrix V times a diagonal matrix with S are the singular values. Okay, so S are these singular values. Here are the singular values for the matrix, these three guys. Okay, oh, you see them here from the singular value decomposition. And this is the matrix sigma inverse, okay, times U transposed. And you see that this is just like the pseudo inverse. So just like pseudo inverse of A. It is a pseudo inverse of A. Okay. So first of all, you see that the SVD, like many other, just like you had with QR, when you have a matrix formula in general, this is kind of a take-home message in general that might be with you in your data science career down the road. And you probably won't be working with matrices night and day, but from time to time you'll come into some new theory or some theory that you haven't used, and you'll read, there'll be some matrices, and what you'll see is, oh, there's some matrix formula, you have some decomposition, you can stick it in the formula and you get a different form. And this different form is sometimes better. So that's what happened with QR, and the same happens here with SVD. So let's see when this is useful. So it's useful when A transposed A, as I was already alluding to, is singular. Okay, this matrix is singular if and only if the matrix A is not full rank. I mean, that's a proof you've seen. I mean, this Gram matrix is always square, but sometimes it's singular, sometimes it's not. So here in this bit of code, all we're doing is constructing, search for a bad example. Okay, that's what we're doing here. So while true, random seed. Now, this is maybe useful if you haven't seen it. It has nothing to do specifically with linear algebra, but at this point, you don't care about linear algebra so much anymore because you're done. You did your quizzes. You care about just being a better data scientist and also creating good projects for this course. So a seed of a random sequence, when you do this, it sets Julia's random number generator with some initial value. And here what we're doing is we're just increasing this initial value by 1. increase the seed. So we're basically going to search for a seed, and every time we get a random matrix of dimensions n and m, just with the entries 1 and 2, and we're going to compute its rank. And we'll say if the rank is less than 3, then we'll say we found a rank 2 matrix. It took us 204 attempts here with a seed. But the good thing about this is now this is reproducible. It's as though we have the CSV file for the matrix. Okay, so that's if we do C204, we get this matrix, and indeed the rank of this matrix is A. Okay, so that means that the rank of A transpose A is also 2. Okay, and the determinant of A transpose A is n0. So if we try to do the inverse of A transpose A, we're going to get a singular expression because this matrix is non-invertible, this Gram matrix. Okay. So what does that mean for trying to solve AX equals B? Okay, or sorry, for solving a least squares problem associated with AX equals B. So we still have a B right-hand side, just so you see it from before. We have this B right-hand side. Okay, and we can still use the backslash operator, A-B. So say, whoa, this appears to have given us a least squares solution. Okay, and if we ask for the pseudo inverse, we still get something which appears to be a pseudo inverse. Okay. So by the way, this is the left inverse of the matrix A, just if you want to see it. So if you do A DAG times A, we should get the identity matrix. So the pseudo inverse is a left inverse. Okay, so this is the identity matrix. And yeah, this pseudo inverse multiplied by B gives us these 29, 44, and 29, which is the same least square solution we got from the black box, from the backslash operator. Okay, but now let's do it ourselves from first principles. So let's do the SVD of the matrix A. Okay, so we get the U matrix, the list of singular values, the V matrix. Okay, that's the SVD. Okay, here are the singular values of the matrix A. Okay. We only have 2 singular values. The third one is 0. Okay, so only 2 singular values. Why is this? The number of singular values of a matrix is exactly equal to its rank. Okay, what's the rank of A? 2. Okay, so only 2 singular values. Now, here is a bit of an issue. So Julia gives us S as these are the 3 singular values, and the third one is this 0. This thing is a 0. Okay, so it treats it as a, well, programmatically as a singular value, but mathematically it's not. Okay, so the number of eigenvalues of the matrix, so if we do, for example, eigenvals of the Gram matrix A transpose A, we're going to get only 2 of them are going to be non-zero, this one and this one. And if we'll do the square root of that, we'll get the singular values. Okay, these are those singular values, is 7.77 and 1.57. Okay, this third guy is a 0. Right, so that's just something to keep in mind. So there's only 2 singular values for this matrix. So let's actually just clean S. Let's filter it. You know, this is throw away zeros or almost zeros. So what we call is an almost zero, something that is not, that does not satisfy this thing of being greater. This is an anonymous function of being greater than 10 to the minus 6. Okay? So these are our 2 singular. What does it do this? Sorry, S was this. Filter X. Did I make a mistake here? 1 second. S is this. Yeah, I don't know why I did that. Okay. So these are the 2 singular values we have. So there are 2 of them, and that's exactly the rank. Now, at this point, what we can do here is this is called the compact SVD. So this is the, well, using the compact SVD for the pseudo inverse. So this is a formula which is exactly let me just bring it from up here so you saw it. I'll just copy it so you have it. It's this one. Okay, so it's, you could compare the formula to what we're doing here. So SVD gives us a V, a U, and a T. So what we're getting is our V, but we don't want here the full V. We don't want the square V. We rather want the V that is only with the dimension of the length of dimension of A more and the rank. Okay, so this is just compare these two. The SVD of the whole matrix gave us this 3 by 3 V. So in Julia, when you do SVD, you get a square V and a square U. Okay, they're not going to be of the same dimension, but just so you see it. So, oops, that's not what I wanted to do. Sorry. Let me just do this again. So this is the V that we got from Julia, and that's a U that we got from sorry, U was not square, but V is square. Okay, but when we are doing when we get these, when we do this thing, so V only collect the first 2 columns of V, so we ignore the 3rd column. Okay, and that's what we're going to use in this thing for the pseudo inverse. So now if we do V, this guy, times the diagonal of 1 on S, that's sigma inverse times that, we get this pseudo inverse. We get this matrix and compare it with the pseudo inverse, and you see that it's the same thing. So the reason of this little demonstration is to show you that you could still use pseudo inverse on systems where on the case that is the bad case that we assumed before, the case that gives you the singular exception, if you were going to just use the formula that inverts A transpose A. Okay, so that's it. Now, to see what's going on, well, we can go back to the normal equations. Now, these normal equations, they result in different ways. So in one way, they can result directly from projection. We actually did this a few weeks back. And in a different way, they can result from, and you did this in the practical by taking the derivative of the norm. So an equation where a derivative of the norm square. So a situation where the gradient equals 0 is any x that satisfy these normal equations. Now, these normal equations don't require A transposed A to be invertible, meaning they don't require A to be a matrix that is with a 0 null space. And if you go to the normal equations, this is a typo, and you replace A, now take again, this is a singular value, yeah, this is the SVD. Okay. So replace A with its SVD. So let me just go straight down here. So I'm going to the normal equations, I'm replacing A with the SVD. Then what you get is you get these nice cancellations because A transposed becomes U. Again, flip the SVD, U sigma V transposed. Okay. Transposed, and that gives you a. I'm sorry, I'm making a mistake here. So sorry about this. You guys are after a quiz, and I'm behaving not nice. So let me just, the SVD is U sigma V transposed. Okay, so here we have in the SVD U sigma V transpose. It's the U that comes first. Right? You can just think of it in the mnemonic in the alphabet, the U and then V. Okay, U sigma V transposed. Okay, so now I'm sticking this thing as U sigma V transposed. Okay, so after you transpose that, the U transpose will cancel the U, etc., and you've got a V sigma squared V. And you've got still this on the right-hand side, U sigma V transpose transpose. So I've stuck the SVD in the normal equations. Now, the this matrix, which we have V sigma -2 times V, is a left inverse of V sigma 2 V transpose. So to see this, just multiply this from the left to this and get the identity. So let's multiply by this left inverse. So multiply by V sigma inverse squared V transpose. And you've got X equals this. And hence what you have is X is V. After this V transpose cancels, you've got V sigma inverse U transpose. So again, this is not the SVD, this is the pseudo inverse, V sigma inverse U transpose. This is a pseudo inverse which comes from the SVD, which is what we calculated above. Okay. So in summary, when you deal with SVDs, you have, at least theoretically, but also practically, so sometimes this is used as a practical algorithm, you have a way to get the pseudo inverse no matter what, whether A is with a zero null space or not. Now there's a question. Sigma is a matrix whose diagonal entries are the eigenvalues squared, but how about the sequence of its diagonal value? Oh, okay. So the question, so in sigma, the sequence, you always put it from, I mean, all these calculations is a good question. So all these calculations, which we did now for a pseudo inverse, would work even if we permute the order of the elements of sigma and hence permute the U and the V. However, when we present the SVD for purposes of compression, like you did with your nice images in the last question of homework 2, we put in the SVD, we start with the highest singular value and we decrease. And the reason of that, we'll actually speak about this more next week, because that's why we get the low rank approximation. But all these, even if we would now going to permute the columns of V, permute the columns of mu, and permute the entries of sigma, permute them all in the same way, all these formulas would work, because we're not using here SVD for the purpose of low rank approximations. I hope that helps, right? So here we're using SVD for a different purpose. We're using SVD simply because it's a decomposition that always gives us a pseudo inverse. At least that's another use of SVD. Okay, hope that helps. All right. Okay, so that's good, but that's very technical. And actually, I must apologize. This is not the type of technical thing I want to show you just after a quiz, because after a quiz, you want to see something kind of a bit more pizzazzy. So we get to this next topic, which is related. This topic is called Corner of Regularization. It's Tikhonov, that's a person. Regularization. Regularization is a big term in machine learning, in data science, etc. And this is what you're going to see now is the most standard, basic, canonical example of regularization. And a different term for that is ridge regression. A different term for that is also shrinkage estimators. And there's more and more terms. So basically, all of chapter 13. No, sorry, is it all of chapter 14? This is chapter 14 of VMLS, and in many places elsewhere. Now, here is kind of a general observation. So the matrix A transpose A. So we're now going to start from a very technical manner. Okay, so we presented here SVD as a way of handling the situation when the matrix A transpose A was singular, and hence you can't multiply by the inverse of A transpose A and get your normal pseudo inverse, your A dagger. Okay. So a different approach, which is at first it might look a bit funny, is you just, instead of A transpose A, add this term, which is lambda times the identity. And think of lambda as something quite small. Okay. So, yeah, lambda again in Julia, you can do \lambda plus tab. get lambda. Okay, that's a letter lambda. So here I'm making a function A transpose A of lambda. So look, if I do, sorry, the function is just called AA. So if I do AA of 10, I can do that, or 10.3, you know, I'm getting some matrix. Or if I do AA of 1.1, I'm getting some matrix. Okay, if I do AA of 0, I'm also getting some matrix. But the problem is this is still the A, where if I do the rank of AA of 0, it's going to be 2, okay? Or its determinant is going to be 0. So it's going to be singular. But what I'm going to do is if I do AA of 0, 0, 1, I'm adding this perturbation to A transpose A, which is actually going to make it full rank. So you could treat this as at first I'm just adding entries on the diagonal of A transpose A, which are multiplied by lambda, and that would make actually A transpose A invertible. Now, this is one way of looking at what's happening with this Corner of Regularization, but I'll actually take a different way and explain it as follows. Okay, and what you're seeing now is a standard way in which it is presented. So we're experts at the least squares problem. We know that we want to approximately solve AX equals B. Okay, and we know also that in a data context, our A will often be, you know, the design matrix and have like values of features, and our B will be actually Y and it will be labels. So the idea of regularization is to add this additional term to the objective, to add this additional term, where lambda is something that's non-negative. So if lambda was 0, lambda is a constant. If lambda was 0, then what we're doing here, we're with the same problem. You agree, right? So ignore this thing on the right. So far, just look at this. So if lambda is 0, you're there with the same problem. How about if lambda was like a zillion, a huge number? What is the best x here if lambda is a huge number? If lambda is a billion, zillion, quadrillion? If lambda is a few Googles, what's the best x that optimizes this when lambda is a very big number? Zero. Why? Because we're penalized. Thanks for answering. So we're penalized here for the norm of x. So if lambda is a huge number, we're saying, oh man, x really costs. X is a painful thing. So lambda captures how much pain we have in x. Okay. Now there's more to this theory, and you might do this when you do the course data 7202. It's not clear, but you might, where lambda here is also a Lagrange multiplier, if you've heard of Lagrange multiplier. So it has to do with the fact that you're basically constraining the problem so that the L2 norm of x is going to be not too big. Okay, but what you can qualitatively see is if lambda equals 0, then you have the normal least squares problem. If lambda grows to something very big, then you know this thing is not going to matter at all, and the best x is just going to be an x0. So lambda is actually your shrinkage parameter. The bigger the lambda, the more you're shrinking x. Now, at first, this might look like a very stupid idea. Why would you do this? Why would you take a perfectly good data fitting problem, which is what I'm highlighting here, and add some other term that's just ruining it? But in fact, this happens to be a very common technique called regularization. So you're adding some regularization to the problem to make sure that the actual data does not completely affect the way you choose the problem, but you're actually dampening the data. Well, you're dampening your fitting procedures. We'll get to that a bit more, to the actual application of this. But at first, okay, you see that this is a thing. Now, you can view this, you can write what I just did as the following thing. You can actually open this up, open the norm, so and I'm missing here an x. Sorry, too many typos here. Excuse me about that. Yeah. So I can take this A and multiply by X. Now this here is a block matrix. What I've done here is a block matrix. So it's a block matrix that has an identity matrix below with a square root of lambda. And this is a block vector which has the B and a 0. So I'm saying that this objective here is equivalent to this objective on the right. And that's in the start of chapter 14, or you can read if you don't see exactly how it is immediately. But it just has to do with the fact that a norm of block vectors is the norm of the normed blocks. Okay, and same for norm squared. So what we have here on the right is a different least squares problem. So ridge regression is nothing but the original least squares problem modified. In the new least squares problem, what we're doing is we're minimizing. Let me actually write this. I'll write this above. So we're trying to minimize the tilde ax minus tilde. Okay, so where the tilde a is not your original a, it's original a with identity stacked below it. Now, if you go through the computation, then you actually see that the least squares estimator is quite similar to the original one. So now you take this tilde a, so this is a pseudo inverse, tilde a transpose times tilde a inverse times tilde a transpose times this b transposed. And if you work with the block matrices, what you get is you get exactly this thing. So you get that you're not inverting anymore a transposed a, you're inverting a transposed a plus lambda I. Okay. And I've shown you above that when you add this lambda I, then this thing is actually non-singular. Now, to actually see this, there's also a different way. So you can just argue and look and see that the matrix A tilde is always full rank. Why is that? Because any vector x that you multiply by the matrix A tilde and require for the solution to be 0 will also need to be multiplied by square root of lambda I. And we're taking here lambda strictly positive in this case. And then this matrix A now has linearly independent columns. So if before A did not have linearly independent columns, by actually sticking the square root of I below it, we have linearly independent columns. Now, this thing is called ridge regression, corner of regularization, shrinkage estimator with an L2 penalty. This is called an L2 penalty. The reason is that it's very common also to add an L1 penalty, and we might get to see that still today. Let's see. So that's called a ridge regression with the L2 penalty. And what I'm going to claim is that when you do this, then you can actually throw in more and more features in the problem. So now, if you remember before we had A, maybe you took one feature, you took a square, you took some other things, you threw a bit of features, but now you can, but you didn't know exactly how many. Now you can throw more and more features, and by actually increasing this lambda, you will decrease or shrink the contribution of each of these features. Okay. Are there any questions about this? I mean, we're teaching here this kind of at a loose level. Let's see it at work. So what we're doing now is we're going back to the problem which was you've seen this before when we introduced least squares data fitting. So there is some reality where you have some relationship between X, which is money invested, and long-term return. And we've been on this notebook before. Okay, so we've done this, and we've done a least squares fit with one line. And here we've designed A as a design matrix. That's A, the design matrix. Okay, and we did a least squares fit. Fine, we were happy. And then we said, okay, well, let's throw in another feature. This feature is not just going to be money invested, it'll be money invested squared. That's a new feature. Okay, so just so you understand, features can sometimes be additional data collected, or sometimes it can be the data that you have where you do some transformation to the data. In this case, the transformation is taking the money invested and squaring it. Okay, And this is something you saw a few weeks ago. And we did this together. We did this new prediction. And here, oh, that's nice. Oh, you got the second order fit. Seems to be a nicer fit. We're happy. Okay. So, and this is how we did it. We created A as this design matrix. Okay. So what if we were now going to go more? Let's take A to be A has more powers. Okay. So just so you see A, here's the design matrix A. It has the intercept, that x to the power 0. It has x to the power 1. It has x squared. It has x cubed, and it has x to the 4th power. Why not? Sky's the limit. I mean, let's throw in more features. Okay. If we do this, yeah, we could still get beta hat. Okay. We can still make a prediction. And look. Wow, look at this. I mean, this is now a 4th order model. So what's bad with what I'm doing now? What's a negative of this process? Overfitting. Overfitting. So if you want to look at the the extreme case of overfitting, so let's share the Statistics with Julia book here. I think you can see the Statistics with Julia book. Yeah, thanks. Okay, so let's go to you have this chapter. I mean, you have the whole draft of the book, so you probably have seen this example here where and I know you had this in one of the practicals with Sam and Walla. So this is like an extreme case of overfitting, right? You've dealt with this when you spoke about the Vandermonde matrix, okay? So this is kind of fitting a polynomial that would fit all the data. This is like the worst case that can happen with overfitting. Okay, so overfitting in general, it doesn't have to be that you fit a polynomial to match every point, but already here, maybe what we did, and that's a lot of the job of the data scientist, is to know the difference between overfitting and doing good model fitting. Okay, so as was mentioned, here maybe we're overfitting, but maybe we're not. So it's not so clear, right? I mean, how do we know if we're overfitting or not? So with ridge regression, we have a mechanism to actually throw in more features and to reduce our level of overfitting by controlling a single parameter. And we like this in data science. We like to have not millions of choices, but we like a single parameter, and that parameter is going to be this lambda. Okay, it's going to be this lambda. What is best lambda? Well, I show you a method to choose best lambda, but that's still an issue of debate sometimes. Okay, so just to see this in this case, so look, now we're going to take powers. You see, this is powers. We're going to get a model, so with many features. So we're going to get x to the power 0, x to the power 0.1, x to the power 0.2, x to the power 0.3, x to the power 0.4, and x to the power 3. I mean, the length of powers, there's going to be 31 features in this model. Okay, so, and here is the beta fit. And here's the y hat for this, and here's a model with 31 powers. Okay, so of course this is a very overfit model. And of course, at some point it goes to infinity. By the way, you have to know every polynomial fit will go when you go far to the right or far to the left, either to positive infinity or negative infinity. That's just the nature of polynomials. Okay, so here it happens kind of very quickly. But this is like almost interpolation. But it's not interpolation because the polynomial interpolation that I just showed you in the Statistics with Julia book kind of gets kind of powers, integer powers. This is kind of powers that are fractional powers. Okay, but still it's a model. So let's say we don't know much about our data set, and maybe we can't even plot it, because often we won't be able to plot the data set because it's too high dimensional. Right? This is a very clean situation where you just have a plot, money invested versus long-term return. But often your features are not going to be, or your bulk features will not just be money invested. There'll be hundreds or thousands of features, or sometimes more. So you certainly cannot create a plot. So what we're going to do is we're going to create the ridge regression fit for that. And we'll do that from first principles. Of course, you have packages for that, but it's not hard to do it from first principles. That's why we have this course. So the ridge beta is going to be, and look, this is just the pseudo inverse with a slightly different A, the A transpose to A plus the lambda I times A transpose times Y vals. Okay, this is going to get us the beta estimate for a given lambda. So if lambda was 0, it's going to give us this estimate. If lambda goes to infinity, as was said here before, it's going to give us all the coefficients are going to be 0. And what we can do is we can vary this over a lambda grid. Okay, and we're actually going to do ridge beta, so we're doing many fits, one for each lambda. Okay, so all I want to show you here is the norm of the beta estimator. Look, when lambda is small, the norm of the beta estimators is huge. Okay, and as lambda grows, as we increase lambda, it's clear that this norm is shrinking. Okay, so our beta estimators are shrinking. Okay, the beta, by the way, is what we had here as when we looked at this equation as an x. Okay, so again, in the data fitting situation, x goes to the features, goes into the matrix A, and this x becomes a beta, and this b becomes a y. Okay. Okay, so when you've got this, you can now choose some specific fit, for example. So let's do, for example, beta of 2000. Sorry, this is with lambda equals 2000. Okay, and now we've got our beta hat, and here's a y hat associated with that, and this will happen to be the fit. So in this fit, there's still 31 features. But we know that we've applied a shrinkage estimator, so we kind of hope that we have an overfit. Okay. Now, your question at this point might be, hey, how do you choose this lambda? Okay, so if I would have done this not with 2000, but I would have done it with 100,000, I'm going to get different estimators. I'm going to get a different estimator here. I'm going to get a different model. I mean, these models, they might look similar, but they're different. Okay, so how do I choose the lambda? Now, for this, there's a method. I suggest go to. I won't have much time to discuss this. So this is something that, for example, last year I didn't discuss. If you go to listing 910 in Statistics with Julia, you could see a cross-validation example where we're doing a ridge regression problem. And what we're doing is we're searching over a grid of lambda, and we're choosing which one has the least loss. Now, the way to do this, how do you exactly do this? So there are different ways. What we're doing here is using a method that you learn about in different courses. You learn about in machine learning, or maybe you'll even hear it in the intro to data science, k-fold cross-validation. Have you heard about this method, k-fold cross-validation? Yes, so, and that's an intro to data science. Okay, good. Okay, so what you can do is you can then go and you can say, okay, I'll do, for example, k-fold cross-validation, and that allows me to then search for the lambda and see which one appears to have the lowest loss, and then you find your lambda optimal. And this is a lambda that you then stick into ridge regression. That's one way of doing it. Okay, so that's what I wanted to say about ridge regression. And of course, there's more to it, but the nice thing is that there's not a whole lot more, because ridge regression is nothing but a normal least squares regression after you've changed your objective to be different. So now that you understand the linear algebra of least squares, ridge regression is nothing but least squares, but regularized least squares. There's a bit more to the mathematics of the story, that actually, if you take the pseudo inverse, that you get this. If you take this as a pseudo inverse, this guy, Okay, that's like a pseudo inverse, which for positive lambda always exists. This thing is always invertible. And if you take the limit of lambda going to 0, what you're going to converge to is the SVD pseudo inverse. And that's kind of nice. So a few minutes before that, we showed the SVD and we said that's always you always have a formula for the pseudo inverse. Okay, so that's kind of something to know. A related topic, which I won't have time to speak about, but there's code here, if you'd like to see, is lasso. So who's heard of lasso? You know, like in the Cowboys. Lasso. Lasso. Has anybody here used like a real lasso? Giddy up. Has anybody used like a real lasso? Like, no, nobody? So lasso is this thing that you go like this and you catch the cow. Oh, okay. So we have somebody that is used, but is modest about their lasso skills. Okay, but this is not the real lasso. So lasso looks just like ridge regression. This is just like ridge regression, except there's one subtle difference. This is not the, oh, Oklahoma. Yeah, you got lassos in Oklahoma. Okay, so, okay, so this is not the L2 norm, but the L1 norm. Now, this looks like a very subtle change. I mean, big deal. We changed the penalty cost for an L1 norm, not L2 norm. Okay, L1, we hardly used L1 in this course, but L1 is just the sum of the absolute values of the beta. L1, yeah. Now, it turns out that when you put here an L1 norm and an L2 norm, when you increase your lambda, you see what happened. Okay, this is not the right curve, but you could have seen like a different curve when we increase the lambda. I mean, this is basically this is not being curved, but here are the norm of the estimators, okay? So this, imagine that I would plot this, okay? Or I just plot plot this guy, okay? So I'm increasing now lambda. Oh, this is a bad. Okay, it's just because they're dropping so quickly. Okay, so plot beta s from 3 to the end. Okay, so this is what's happening. Okay, so I'm increasing lambda. Okay, sorry, I don't want to waste time on labeling this. With ridge regression, increasing time on lambda, and things are just shrinking smoothly. Well, that's kind of good, but it keeps all the features in there. The reason that statisticians and data scientists like lasso so much, and you'll learn about it more in other courses, is when you're increasing with an L1 penalty term, when you're increasing lambda, then at discrete breakpoints of increasing lambda, so as you increase lambda, the number of non-zero beta actually decreased. So it actually gives you a very natural and beautiful way to do model selection. So you can read about it more in Statistics with Julia or anywhere else if you'd like, and that's lasso. Now the negative from our perspective, so we're now, especially after quiz 3, where we as you are linear algebra experts, so lasso goes beyond. So it's not just least squares fitting, you actually need iterative algorithms, and the mathematics is more complicated. But if you want to understand lasso, well, you first need to do this course, and you did, so good job. So that's what happens with lasso. But as a black box, you can use it. You can just say, I increase lambda, and the variables will decrease like that. Okay, so you'll actually, yeah, that's a point. All right, so coefficients will zero out. So every time you have a drop here, a coefficient of another variable zeroes out. Questions about that? Okay, so there's always not enough time, but now we're going to the next thing, which is kind of cool, and that's classification. I mean, classification is maybe one of the reasons that you're here in this data science degree, because it's one of the big things that happened with machine learning and data science in the past decade. I mean, it's been around for a while, but that's a fact that machines can actually look at things and say, oh, this is a dog, this is a cat, this is an apple, or this is a digit 3. Okay, and of course the oh, there's a question here. Do we need to use them in the final project? Yeah, so in your final project, if you're, let's see, so Yeah, I mean, to use what? Sorry, what's the question? To use what? I'll speak more about the final project also in next week's lecture. Okay, and yeah, also feel free to come to the consultation hour this week to ask about the final project. So I'm not sure what the question was. You need to use what in the final project. But yeah, if your final project, let's just look a second very quickly. I don't want to waste time on this. So if your final project is on the topic of classification, then what I'm speaking about now is very much related to that. If your final project is on the topic of multi-objective and regularization, topic 5, then that's what we spoke about in the past 45 minutes. Okay, so yeah, today we're touching both of these. Okay. And I'll speak about these other topics more in the next lecture. And perceptron, we're pretty much done. But I'll give more insight for the final project in next week's lecture. Okay, so what I want to do in the next couple of minutes is I want us to classify digits. Okay. Now, just some stuff. This here is Flux, is the Julia machine learning package, but we're only using it to get the data. And what we're getting is this, this array, which we call here images, which has 60,000 images. And these specific images are from the MNIST data set. Okay, so the MNIST is a common standard data set. This is the most basic data set you use for elementary machine learning. And there are many MNIST data sets, but this is the MNIST digits. So there's 60,000 digits of images. So look, if I go, for example, to images, this is an image. What's this digit? I think it's a 1. Okay. And if I go to a different one, then this one is 2. Okay, I'm with you. It's a 2. Okay, etc. Each image is 28 by 28, and of course Julia shows us this images kind of nicely because I don't know, type of images is it's an array of gray fixed point numbers, and Julia knows how to show it like this as an image. Okay. Now, each image, if so, somebody said that this image is a 2, so let's go to labels 445, and yep, it's a 2. Okay, so when you want to do machine learning, you need your supervised learning, you need your data to be labeled. Okay, so the features here are all of these pixels for an image. There's 28 by 28. I believe that's 784. Okay, so 784 pixels. Okay, and each pixel has a value maybe between 0 and 1. Okay. So you can treat an image as, this image is a 784 dimensional vector. Okay. Now, what we want to do now is just use basically squares for very simple classification. And this is not going to be cutting edge classification. So the top of the line with the MNIST data set is something like 99.7 or something like that % accuracy. That's as good as you can get with your best neural network. So we're not speaking about, but we're just going to use least squares. So we only have 6 minutes. Let's do it. Okay. So what we're going to do is we're not going to classify, we won't have time to do the multi-class classification to say if an image is 0, 1, 2, 3, 4, 5, or 9. We're only going to distinguish between 3 and 8. Okay. So what we're going to do is here is we'll take all of the images that, and by the way, the data set has a train set and a test set. So there's 60,000 training images and 10,000 images that are considered for testing. Okay, so we're only going to take the images that are 3, and we're only going to take the images that are 8. And this is, we're going to select the images if their labels is 3. Okay, so this returns this is a Boolean array of length 60,000 when I do this. Okay, 60,000 zeros and ones, where approximately 1 in 10 is a 1. Okay, it's a 3. So we're only going to select the 3s, we're going to select the 8. So we have a quite similar number of 3s and 8s, about 6,000. Yeah, it's about 10%. About 1 in 10 is a 3, and 1 in 10 roughly is an 8. Okay, so here's the 54th 3. Here's a different 3. Okay, this is another 3. You got all kinds of 3s here. If you're interested in what 3s looks like, go to this array. Okay, and similarly with the 8. All right. So here is how we use now least squares in a very barbaric way to do this classification. What we're going to do is we're just going to do least squares data fitting, where for the y values, we will put -1 for a 3 and +1 for an 8. Okay, -1 for 3 and whoops, what did I do here? And +1 for 8. Okay, so I'm going to create this y val. So sum of these two guys is 11,982. I'll say I'll have -1, -1, -1, -1, -1, -1, -1, and then ones. Okay, why? Because then I'm going to stack my data matrix and I'm going to put all the 3s and afterwards all the 8s. And when I stack it, I'm going to take each of these images, I'm going to unravel it from a 28 by 28 array. I don't even want to call this a matrix, from an array to a 784 long vector. I'm going to vectorize this image into one long vector. Okay, this is a y vals. So then the A, this is A of least squares. This is the design matrix. I'm going to use some VCATs and ACATs, etc., but just see what happens with this A. So after I run this A, and oh, come on, why are you doing this? This is not good for us. Let's do this N and this A. Okay. So what I'm going to do with this A is I'm going to get here the, look, it's like the design matrix, which is not much different than, I'll go now to design matrix for a much simpler problem. Here was a much simpler problem, just so you see where in context. You see, you had here 3 features, 1, x, and x squared, okay? And you had as many observations as you had, n, okay? This was the A when you did just this little quadratic fit. Now, the number of features which we have is 785. 785. Why do we have 785 features? We have 1 for the intercept, and then 784 is 28 by 28. Okay, and this is a number of observations. Okay, I can plot the A, but that's not so interesting. So the reason I'm plotting is to see this plot is, you know, you got around the edges a lot of 0. And this A has, I mean, all this stuff, all these VCATs and HACATs, that just took our images and kind of, well, convert them first of all to floats out of an image and then vectorize them. Okay, now all we're going to do in terms of fitting is this. And I hope this will make you appreciate least squares just a bit. So simply least squares fit to A beta approx y val. Okay, we would like A beta to be y vals. We would like beta to give us something which is +1 for a, I guess it was an 8, and -1 for a 3. This, let's run this, time it, and it should take around 3 seconds. So it took 5 seconds now. I don't know, my computer's tired. Okay, and this was beta. You see here a lot of zeros, but it's not, they're not all zeros. So if I just plot, just to get a plot for beta hat, you know, there's a lot of things are zeros, so a lot of pixels don't count, but there are a few pixels that count a whole lot. Okay, and some of them count positively, some of them count negatively. Okay, I mean, I can sort the beta hat, I can do things like that. But now let's see how we use this for classification. So you see, if I do this, decide is going, this is a function. The function decide is going to get an image. All I'm going to do is I'm going to do the inner product of this beta hat, of this thing which I've trained. This has 785. And by the way, this was not training by gradient descent. This was one shot doing least squares fit. Okay. Of course, if this was a huge problem, you'd need gradient descent. You'd need other methods. Okay. But this was one shot least squares fit. Okay, so I'm getting, this is the image. This here is just vectorizing the image, appending a 1 for the intercept, and doing beta hat. Now here I'm asking if it's positive, if my predicted value for the image is positive, then let's say it's an 8. If negative, say it's a 3. Okay, so if positive, 8, otherwise 3. I'm done in a second. Okay, so that's a function decide. So let's take some image. Let's take the the 24th 8. Okay, and let's apply decide to this guy. Let's apply decide to this guy. Decide on it. We did it. We did it. Let's try the 244th 8. It also worked. Let's try the 244th 3. It worked. Let's try the 44th 3. It worked. Let's try the 22nd 3. It worked. Let's try this 3. Well, there's not such a 3 maybe. Let's try this 3. It worked. Let's try this 3. I guess again, we don't have, I thought we have, oh, okay, this is on the test images. Okay, there's only around 1,000 test images. So let's try this 3. It worked. But however, if we try now here, look, this for these ones, if we decide the first 8, we get an 8. If we decide the first 3, we actually make a mistake. We get an 8. So look at what the first 3 looks like. The first 3 looks like this. And our classifier thought it's an 8. Dummy classifier. Well, we're smarter. Good. We know how to see numbers. Okay. And if we count, then basically we get this thing which says that we've classified 968 out of the 3s were 3s and these were 8s and vice versa. And this is a confusion matrix. And our story pretty much ends here. Now, we can't get this human level accuracy with least squares. However, you should be proud that you know fully everything that works in least squares, so you can make a classifier from complete scratch just by adding, subtracting, and working with matrices. And you can go to this code listing 9.5 in statistics with Julia, and that does it for a multi-class classifier, which achieves 86% accuracy and this confusion matrix. So we're out of time, but we'll continue next week with a whole bunch of these fun applications, mostly around the project and a few last tidbits. Any final questions? No? Okay, so well done on pushing on the quiz, last quiz, and see you next week or in the visit hour. And, oh, there was a question, can we have the solution for question 3? If the quiz, you mean? Yeah, there'll be a full solution for the quiz posted shortly. And it will be the topic of the practical as well. Okay. All right. All right. See you guys. Have a good night. Bye-bye. Or good afternoon if you're in Asia.